Welcome everyone. We're continuing with our exploration of momentum, and today we're going to look at collisions and explosions. Sounds quite violent, but it really isn't, okay? It's a really nice section. So let's just remember where we've been, okay? So what we're going to think about in this section is, why does a rifle move backwards when you shoot it? So you shoot it, you know the bullet goes forward, but if you don't shoot it properly, it can do a lot of damage, okay, especially big rifles. So, but why? Why does it have to move backwards? You can't actually shoot a gun without there being recoil, okay? And also, when you have ice skaters that are on ice and they push against each other, why do they go backwards? Why do they move apart? What is it that causes that? These are all things where we're now going to investigate how that works. So we're looking at these with the rifle. That's an explosion. The ice skaters are also an explosion, but we could have a collision there as well. With the way I ice skate, it would be a collision, but we're not going to worry about that. So remember, we've worked through a lot of this already. So we've done the definition, the equation, properties, Newton's laws, changing momentum. Today we're going to look at the conservation of momentum. All right? Keywords, things you need to take into, that you need to remember. I'm just going to do this, I've got this all the time. There we go. All right. We're going to look at the word isolated system. You should have heard this term before, but I'm going to go through it in detail so you know. We're then going to look at the conservation of momentum. You should know what conservation means because you've heard it in terms of energy, and we know what momentum is, so we're going to put the two concepts together. And then we're going to look at collisions that could also be explosions, okay? In this section of work, when we talk about a collision, we could also mean an explosion. They go together. It's the same type of situation, okay? So, there we go. I've got the explosion. Sometimes I get a little ahead of myself. Now, let's look at conservation of momentum. So first of all, what we're going to look at with this is we need to define what an isolated system is, okay, because it only happens in an isolated system. We then need to talk about what do we mean when total momentum remains constant. Remember, we're dealing with vectors. And then, with the total momentum remaining constant, we're going to consider the size of the total momentum and the direction. Now, that's something new in terms of your conservation laws. You haven't done a conservation law yet that involves a vector. You've only done one that involves a scalar, which is energy, okay? So here we're going to have to put our thinking caps on so that we can keep track of what's happening with the direction, because momentum's a vector, so direction is very, very, very important. Okay, so what is meant by an isolated system? So first, let's split this up into what the words mean, okay? So when you hear the word isolated, what do you think of? So if we say somebody is at home isolated, okay? Or they're stuck in the middle of the ocean and they're isolated from everyone else. What do we mean? We mean they are on their own, okay? They're alone. So we would look at it, so from an English point of view, we would go, they're alone. They're the only thing that's there. So if I'm talking about an isolated system, I'm taking a system and putting it on its own. So I'm taking all the factors around it and I'm ignoring them. Okay, I'm taking them out of the equation. A system is just the situation we're talking about. So here we're talking about collisions and explosions. So when we have two objects colliding, or one object exploding, that interaction between the objects, that's my system. And I'm taking it from the big picture, so from everything that's hanging around it, and I'm only going to consider the small little section. That's the system. Okay? So, let's define it nicely. A system is defined as a small part of the universe that we consider when solving a particular problem. So, we know the universe is very big. If we try to consider a big part of the universe when trying to look at a collision, wow, the maths and all the other things that comes into play would just be way too difficult. So we narrow it down to just the objects, the things that are involved in what we're doing. Also, at this level, we ignore a lot of extra factors because we don't quite have the maths yet, okay? And that's fine, because at school level, we're trying to teach you the foundations. We're giving you the principles so that when you go study physics at varsity, at university or college or whatever, you have the foundation that they can then add on to, okay? By an isolated system, this is now the important definition. It's one that has no net external forces acting on it. Now, I haven't just said net force. We know what a net force is. It means that an object will change its motion. When we have objects colliding or exploding from each other, they're definitely going to change their motion. But I've been specific here and I've said external forces. What I'm talking about here are forces like friction. Okay? Friction's an external force. So we're ignoring friction. We're going to say, nope, we're not going to worry about friction, simply because when we look at two objects colliding, we're actually only concerned with that little moment in time when they do collide. So the friction they may be feeling on the surface they're on, it's so small and for such a short period of time that, well, we can ignore it. Okay, so here, an isolated system means no net external forces. You have to use the word external, because there are going to be forces in the system. All right, so because when the objects collide, one object's going to push on the other. Newton's third law. Those forces can't disappear. Otherwise, the objects won't change their momentum. All right? So, what do I mean when I say total momentum remains constant in size and direction? Size is easy because we can calculate the momentum of the objects before anything happens. We can calculate the momentum afterwards. And magnitude's easy to compare. Direction, though, is something new. And direction is very important because we're dealing with vectors. So when I calculate the momentum of my system, originally, that momentum has to have a direction. It has to be going somewhere. After something happens, the momentum total needs to be the same, and the direction needs to be the same. So when I first do this, if I say that it's going to the left, it must finish going to the left. It can't change direction because then something's gone wrong. Okay, it's just one of those things with momentum. It's quite easy to prove, but it's got to be constant in size, magnitude, and direction. Okay, so this gives us the principle of conservation of momentum. This they love to ask. Total linear momentum. I've underlined total linear because it's the thing you leave out in your exam. You'll tell me that the momentum of an isolated system remains constant. No, we've got to be specific about what in the momentum. So it's the total. Now, we generally only use 2 objects, but it could be 3, it could be 4, it could be 700, heaven forbid, okay? But the word linear is very important. We only deal with momentum that happens in the same plane. So generally, it's going to be horizontal, okay? So we'll have 2 objects moving horizontally towards each other, and hitting or exploding from each other, but they have to be in the same plane. So I can't have one coming down and the other one going sideways. They don't go off at angles. Okay, we don't do 2-dimensional momentum. Even though we don't do 2-dimensional momentum, you still have to put the word linear in your definition, okay? So this principle says to us that the total linear, by using the word total, that means size and direction, remains constant. It doesn't change. When it comes to the equation, we're going to spend more time on this just now. I'm hoping you've seen the sigma sign before. That sign means sum of, okay? Sometimes we'll write this as total momentum before. So if that's easier for you to write instead of the sigma sign, because it's got to look like a sigma sign, it can't be an E, all right? You can also write it as total P after, and I'm just going to go up there. All right. So we're going to deal with that soon and how we work with that, okay? So we've had a bit of an introduction. Lots of things to think about. We're going to take a short break, and when we come back, I'm going to show you how these collisions work. So I'll see you in a couple of minutes.